So in this video, we're going to be looking at how to convert surfaces in rectangular coordinates into parametric form. Now, a function in parametric form is typically going to have two variables instead of three, but they're going to be spread out over three coordinates. So that's will get us our three-dimensional surface. But since it's a surface, we're only expressing it in two dimensions because that is a plane. So just as with parametric curves, curves are essentially based on a single dimension, but then you express them in either two or three dimensions in order to get that spatial or plane effect. Now, a lot of similarities exist between writing parametric curves and writing parametric surfaces. And so we're going to start with the sort of most obvious cases, and then we're going to work our way up. A lot of these examples are going to have sort of their analog in parametric curve land, but then because we're working in surfaces, we're also going to be able to appeal not just to things like relationships in polar form, but also relationships in cylindrical and spherical form. All right, so if you have a surface which is expressed as an explicit function, z or any of the other variables in terms of the other two, then it is a very straightforward process to create a parametric surface. You simply let your two independent variables become u and v, and then your third coordinate then is simply that whatever that missing whatever that function happens to be. So let's start with a specific example. Let's say I have actually let's switch it around. Let's say y is equal to x squared plus z squared. Now this is a parabola, it's a paraboloid, but instead of being facing upward, it's facing along the y-axis in this case. So in this case, what we would simply do is we would let u equal x, and we would let v equal z, and then for our y coordinate, we would simply plug in our y in terms of now u and v. So in our x coordinate, we would just say that this is our function of u and v is just u. And in the z coordinate, our function of u and v is just z. And then in our y coordinate, we would simply substitute u and v into our equation. And so we would end up with u squared plus v squared. And then that would become our parametric surface. So again, if you have one variable explicitly solved in terms of the other two variables, then this is a straightforward process. And this is exactly what we would do in parametric curves. If we are in two dimensions, for instance, and we have y as an explicit function of x, we let x equal to t, and then we substitute t into our y equation, and we get our curve. Now, obviously, we're not always going to get a situation like that. So what do we do in some of these other more uncommon circumstances where we don't have a function, or we aren't specifying all of the variables, or what have you? So let's consider an example where we have only two variables. Let's say we have x squared plus y squared is equal to, let's say, 4. Now, what kind of a surface is this? Well, the surface that we have here in two dimensions is a circle, but the z variable is not in the equation, which means it is free to be whatever it wants. So this is actually a cylinder. It's as a surface. Now, the x and y coordinates, we are going to copy what we did from the two-dimensional case with one variable, and then the missing component will simply be our second independent variable. So in the y coordinate in the two-dimensional system, we basically would say x is r cosine t and y is r sine t. Now, in this case, we're not going to do exactly that. We do have a constant radius, so that's not a variable, that's a constant. So 2 cosine, but instead of t, I guess just to be consistent with our notation, we're going to use u, and then y would be 2 sine u. And then the z coordinate would just be the remaining independent variable. So now what are we going to get when we plug all of this into our surface? Well, x is going to be our 2 cosine u, and y is going to be our 2 sine u, and z is v. We can't leave out the z coordinate, the second variable. We can't leave that out because then it's only a curve in the plane and not a surface. So you have to have two variables in your equation in order to get a surface. So if you have a variable that is missing, then that becomes your second variable that is free. Now let's think about another example. Let's say we have a cone. So here we have z squared is equal to x squared plus y squared. Now, if we were to think of this in polar form, in cylindrical coordinates, this would be z equals r, because we would get z squared equals r squared, and therefore take the square root of both sides, you get z is r. Now, we still have this x squared plus y squared, so if we think about our coordinates in terms of, again, in terms of polar, we might be thinking, okay, well, x is going to be r cosine u, again, u instead of t because of our coordinate system, and y is equal to r sine u. We can still do that, except r is not a constant, so we can't replace it like we did in the previous example with just 2 or something like that. Instead, we have r is z. So what we're going to do is we're going to let that r equal our other variable. So now if we go back and recreate our equation, we're going to have not 2 cosine u, we're going to have v cosine u. And not 2 sine u, we're going to have v sine u. But then z is still v. Not because it's free entirely, because it's in both of these other coordinates, but it is that third variable that is defining where z is. All right, and then finally, we can also think about this in terms of what if we're looking at a sphere. So let's think about our x squared plus y squared plus z squared equals, let's say 9. Well, we're going to use polar coordinates in order to do this conversion. So recall that our x coordinate in polar is equivalent to rho cosine theta sine phi, and y is rho sine theta sine phi, and z is rho cosine phi. Now, rho, because this is a sphere, is a constant, and so we can just let that be equal to our constant 3. And then theta and phi can be our u and v. So what are we going to end up with? We're going to end up with 3 cosine u sine v. And we're going to end up with 3 sine u sine v. And then we're going to end up with 3 cosine v.